we have developed a powerful integral, the Lebesgue integral. One nice side effect of our construction is that we can get a solution to the problem of measure. Recall that the problem of measure asks us to assign for any subset of the real numbers a length. This length should agree with the length on intervals. The length of an interval AB is just B minus A, irrespective of whether A or B is there in that set or not. We want to find a countable additive notion of length that agrees with the length on intervals. The solution is to observe that if AB is subset of R, let's say for concreteness sake I'm taking the open interval AB, then B minus A is just integral of 1 on R, on A to B. B minus A is just the integral of the function 1 on from A to B. So what we now do is you consider a new function which is, we define it to be chi AB. This function is defined to be 1 if x is in AB, 0 otherwise. Then it's clear that B minus A is nothing but the integral of chi AB over R. Okay, easy check. So you can obtain the length of an interval by integrating this associated function. So this prompts the following natural definition of that of a characteristic function. So this is called characteristic or indicator function. Let S subset of R, we define the characteristic or indicator function of S to be the function chi S, which is defined to be chi x of x is 1 if x is in S, equal to 0 if x is not in S. Okay, now the name characteristic or indicator function of S is self-explanatory. At any point of the set it gives the value 1, otherwise it gives the value 0. Let me make a side remark here. In the measure theoretic approach to integral, you already have a notion of measure for sets. Once you have the notion of measure for sets, you can define the integral. You can define the integral of this chi S to be just the measure of S. So essentially what will happen in the classical treatment of measure theory first and integral second is the reverse of what is going to happen now. What we are going to now do is define the measure of a set to be the integral of the characteristic function. So let's make that formal definition. This is measure of a set. Let S subset of R, we say S is measurable if chi S from R to R is in M of I. So if the characteristic function of the set is measurable, then we say the set itself is measurable. Furthermore, if chi S is Lebesgue integrable on R, then we define the measure which we call traditionally mu of S is by definition just the integral over R of chi S. If S is measurable but not integrable. But chi-s is not integrable, then mu of s is by definition plus infinity. Okay, so the only way by which the characteristic function, which is a non-negative function, can fail to be integrable on R is if it's sort of going to take an infinite value. That's the motivation behind defining mu of s to be plus infinity if the characteristic function is measurable but not integrable. Now, immediate example, you can see that mu of R is plus infinity. Then mu of any interval of the type minus infinity a is also plus infinity. Mu of ab is going to be b minus a, etc. Okay, so in other words, the function mu agrees with the length on intervals, and this is rather straightforward to see. Now, is there any other larger class of measurable sets, and what is the measure of such sets going to be? Well, the next simple proposition sort of is very basic and tells us that sets of measure 0 are A measurable and B their measure is 0. If that weren't the case, the nomenclature given by mathematicians would be extraordinarily stupid. So let S subset of R be a set of measure 0. Then S is measurable and mu of S is 0. Conversely, if S subset of R is measurable and integral of chi-s is 0, then S is a set of measure 0. Okay, let's prove both parts. Proof: suppose S is a set of measure 0. Okay, then chi-s is 0 almost everywhere. This is just by definition. The function chi-s is 0 almost everywhere. We have already shown that if a function agrees almost everywhere with an integrable function, then the function is integrable and the integral values agree. We had shown this once, as part of when we developed the theory of the Lebesgue integral and convergence theorem, and the integrals agree. So therefore we immediately get that integral of chi-s is 0 as claimed. So a set of measure 0 will be measurable, and in fact mu of s would be 0. Thank God. Okay, now for the converse. Conversely, suppose chi-s integral over R is 0. Okay, now what you do is you define this function fn of x to be just equal to chi-s of x. That is, fn is just chi-s. Okay, and look at summation chi-s of x. Look at this summation. Now notice that if you call this so what you do is, instead of defining Fn to be chi-s, define Fn of x to be summation n equals or rather summation k equals 1 to n Fn. Okay. Now notice that Fn's are non-negative, and integral of Fn is just integral summation, first of all, integral k over r k equals 1 to n chi-s, which is just integral over r, but summation is now outside k equals 1 to n chi-s, which is 0. Okay, so each integral Fn is 0. Consequently by the monotone convergence theorem, this summation Fn, this function n equals 1 to infinity, this converges almost everywhere to a integrable function whose integral is 0. Okay, this is just the monotone convergence theorem. So if you take an element x in S, then clearly the series does not converge. This means that S is a set of measure 0, because this series summation Fn must converge outside a set of measure 0. It does not converge on S, consequently S must be a set of measure 0, as claimed. Might look like a roundabout way of showing it, but nothing really deep is happening. Excellent. Now we have got a nice collection of sets that are definitely going to be measurable. They are all the sets which are sets of measure 0. We want to enlarge and see that this collection of measurable sets is in fact large. In fact, it will be so large that the only way to construct a non-measurable set will be to appeal to the axiom of choice. Please revisit some remarks I made when we showed that the set of measurable functions is in fact closed under taking pointwise limit. It's very hard in practice to land up with a non-measurable function. It's equally hard to land up with a non-measurable set. For all practical purposes, you can assume that all sets are measurable. Anyway, we still need to see some examples, some concrete examples of measurable sets which are not just intervals or sets of measure 0. Also, just one example, if A and B are both measurable and A subset of B, then you can check easily that mu of A is less than mu of B. This just sort of follows from the monotonicity property of the Lebesgue integral. Okay, keep this in mind because this will be repeatedly used without mention. Theorem. We are going to show that some natural set theoretic operations do not take us outside of the class of measurable sets. If S, T subset of R are measurable, then S set minus T is also measurable. And if Si and if Si subset of R are measurable, then so are union I equals 1 to infinity Si and intersection Si I equals 1 to infinity. Countable union and countable intersection of measurable sets are measurable. For computing the measure of this union, just wait a moment. The next theorem that we study will sort of tell you that there is some sort of additivity, which is very nice proof. For the first part, it's just a simple observation. Observe that chi of s minus t is just chi of s minus chi of s times chi of t. To see why this is true, note that chi of s minus t is not 0 precisely if you have a point of s which is not also a point of t. That's why we are subtracting chi of s into chi of t. Chi of s into chi of t will be non-zero precisely on s intersection t. So chi of s minus t is chi of s minus chi of s into chi of t. Now by assumption chi s and chi t are measurable. They are measurable and therefore so is the product chi s chi t, because we have proved a proposition that says that any continuous combination of measurable functions is measurable, and so is and chi of s minus chi of s chi of t. Excellent. So this shows that the difference of two measurable sets is measurable. Now coming to the union and intersection, that's actually easier than this. Notice that if you define un to be just union I equals 1 to n si and vn to be by definition intersection I equals 1 to n si, then chi of un is nothing but max of chi s1 to chi sn, and chi of vn is nothing but the minimum of chi of s1 to chi of sn. Well, the easiest way to see this is to close your eyes and contemplate it for a few seconds and you will get it. There is no explanation I could give that will convince you of this. It's so trivial. Okay, now that you have this, each chi un and chi vn are measurable, being the maximum and minimum of measurable sets. Again, recall that any continuous combination of measurable functions is going to be measurable. Okay. Furthermore, if you define u to be union I equals 1 to infinity si and v to be intersection I equals 1 to infinity si, then this chi un obviously converges to chi u and chi vn converges to chi v, right? Which shows that chi un and chi u and chi v being limits of measurable functions is measurable. This is one nice property of the class of measurable functions. Being limits of measurable functions are both measurable. So this concludes the proof that countable unions and countable intersections of measurable sets continue to be measurable. Now we want to deal with that main property of this Lebesgue measure, that is that of additivity. What this additivity says is that if you take two disjoint sets, then the measure of the union is the sum of the measures, which is natural. We will now first prove it for two sets, then later extend it for a countable union. This is a powerful property and this is very useful in proving various stuff about measurable sets. If A, B subset of R are disjoint measurable sets, then mu of A union B is mu of A plus mu of B. Okay. Note that no assumption is made about whether these sets are going to have a finite measure or not. No such assumption is made. Proof. Well, first of all, A union B is measurable. We have just shown that. Okay, and because of the disjoint nature of A and B, this union, if you call it S, chi of S is just chi of A plus chi of B. Okay, now suppose chi S is integrable, then both chi A and chi B are less than or equal to chi S. And since these are already measurable, this means chi A and chi B are integrable. We have already seen that any measurable function whose absolute value is dominated by an integrable function is integrable. So this means chi A and chi B are integrable, and it follows that integral of chi S over R is just integral over R chi A plus integral over R chi B. This is just by the additivity property of the Lebesgue integral. So in other words, mu of S equal to mu of A plus mu of B. Now if chi S were not integrable, then by definition mu of S is infinity, and either chi A or chi B must not be integrable, because if chi A and chi B were both integrable, then chi S would be integrable, because chi S is just chi A plus chi B. Okay, which means either mu of A or mu of B or even both is plus infinity. So with this additivity holds even in this scenario where one of the sets is not going to have a finite measure. Okay, so immediately by induction, so we are done with that proof. So immediately by induction we get that if AI are pairwise disjoint measurable sets, then you get that some mu of union I equals 1 to n AI is just summation mu of AI I equals 1 to n. This is just obtained by the previous theorem just by applying induction. Okay, now the question is, what if you had I equals 1 to infinity? If you had infinitely many, countably infinitely many measurable disjoint sets, is it still true that the measure of the union is the sum of the measures of the individual sets? Well, thankfully this is also true, and this will be the major theorem of this section. This is the countable additivity of the Lebesgue measure. So it states the following: let AI be a countable pairwise disjoint measurable sets. Then mu of union I equals 1 to infinity AI is just summation mu of AI I running from 1 to infinity. So we have countable additivity of the Lebesgue measure proof, and all of these proofs are just standard, somehow try to apply a convergence theorem. So you define Tn to be just union I equals 1 to n of Ti, and you consider chi n to be just shortcut for chi of Tn, and T you define it to be union I equals 1 to n. One second, I made a mistake here. This is AI. So T you define to be I equals 1 to infinity AI. Okay. Then by finite additivity, which we have just established, mu of Tn is nothing but summation I equals 1 to n mu of ai. This is just by finite additivity. Okay. Now the goal is to prove that mu of tn converges to mu of t. Right. Now because tn plus 1 contains tn, we get mu of tn is less than or equal to mu of tn plus 1. This is just by the monotonicity property of the Lebesgue integral, which we have already mentioned. So this collection mu of tn, or the sequence mu of tn is a monotone increasing sequence. Monotone increasing sequence. Okay. Now again we'll have to split up into two cases. Case 1 mu of t is infinite. Now this means that integral essentially what does this mean? This means that the function chi of t is not integrable. Okay. Now observe that chi of tn is a monotone sequence of functions that converge to chi t. But since chi of t is assumed to be not Lebesgue integrable, that means the hypothesis of the monotone convergence theorem cannot be satisfied. Hypothesis of the monotone convergence theorem cannot be satisfied, because the conclusion of the monotone convergence theorem is that the limit function is integrable. Since we are ending up with a non-integrable limit function, the hypothesis cannot be satisfied. Now what were the hypotheses of the monotone convergence theorem? Well, the hypotheses were, translated to our particular situation, each chi tn is in L of I. That was one of the hypotheses, and this collection integral chi tn, this is a set that is bounded above. Right? So one of these will have to fail. Well, if chi of tn is not in Li for some n, then by definition mu of tn is plus infinity. We already have mu of t is plus infinity. That's our global assumption in this case. So put together we will get mu of t is limit n going to infinity of mu of tn. Okay, in this scenario. On the other hand, it can happen that this integral of chi tn is unbounded, is not bounded above, which just means that mu of t is limit n going to infinity of mu of tn. So in either ways by which the hypothesis of the monotone convergence theorem can fail, in both scenarios we end up with mu of t is limit n going to infinity of mu of tn as required. On the other hand, if case 2 mu of t is finite. Okay, this means that chi t is integrable. Consequently, each chi tn is also integrable, simply because chi t dominates chi tn and chi tn is measurable, which just means that by monotone convergence theorem, limit n going to infinity of chi tn is equal to chi t. Okay. In fact, we cannot use monotone convergence theorem for this. We need the dominated convergence theorem. By dominated convergence theorem, limit n going to infinity, chi t n equal to chi t. Excellent. So this concludes the proof. So we have countable additivity of the Lebesgue measure. So let me just summarize a bit of useful information by giving a definition. Let P subset of power set of R be a collection of sets. We say P is a sigma algebra if it is closed under countable union, complements, and if empty set, R are both elements of P. A collection of sets such that the empty set, the whole real numbers, and this collection should be closed under countable union and complements. Closed under countable union and complement means if S is an element of rho, then R minus S, or let's call this P, not rho. If S is an element of P, R minus S is also an element of P. If Si are in P, then union I equals 1 to infinity Si is also in P. Okay, so why am I making this definition? Well, it can summarize all the properties that we have. The function, so define P subset of power set of R to be the measurable sets. Then we can summarize everything that we have done in this video by saying this P is a sigma algebra and mu from this P to R plus union 0 is a countable additive function on P that agrees with length on intervals. Okay, and P is a sigma algebra that contains all intervals. We can summarize the entire discussion here. So of course the fact that the empty set and R are measurable is rather obvious, and the fact that we have countable additivity we have just shown. The fact that the sigma algebra is just a consequence of the fact that R is there in this collection P and it is closed under complementation, which we have already shown. So in the measure theoretic approach to constructing the Lebesgue integral, we start with the sigma algebra and try to construct a measure on that sigma algebra, and then from that measure you try to go to the integral by defining the integral of a characteristic function to be just the measure of that set. And then we proceed to define what are known as simple functions, which are just linear combinations of characteristic functions, and then you take the limits of such functions and then define the integral in more or less a similar way to what we have done. So this is an alternative approach to the theory of measure going via integrals. This is a course on real analysis, and you have just watched the video on solution to the problem of measure.